Good morning, everyone. I am K. Tarakeshwar and I'm representing West Planet Dubai alongside my co-authors Niranjana Venkatesan and Dr. Adarsh Ganeshan. Today, we'll be looking at a fundamental paradox in model artificial intelligence systems. All of us require edge computing systems like in autonomous vehicles or like smart medical wearables. We need all of them to possess like high performance. We need them to be rapidly quick. We need them to have real-time perception. But the underlying math behind the whole deep learning systems are really too outdated, you could say. They're too old-fashioned. So we need some less energy intensive systems that can actually represent into this in an efficient format. To solve this, we present our work, which is energy efficient framework for rate time encoded multi-class pattern recognition. So this is a proper pattern recognition problem that is a key area which we're focusing on. But the main goal of it is to create a system which is actually energy efficient while also creating a balance with the accuracy so that it matches along our baselines with artificial neural networks. So to do this, we first enter on what our neuromorphic domain is. So the neuromorphic era or the neuromorphic computing, what exactly it is. So I would like to look at our solution this way. So traditional neural networks have always been like a continuous activation of signals. By continuous, I mean that the signals that are produced are discrete in nature, and these discrete signals cannot actually process rapidly because it has to keep on doing all the time. This makes it more energy intensive. But what exactly does neuromorphic computing do? It produces a spike only when there's an event. This way, the number of spikes and the energy used is drastically reduced. But on theory, it sounds really good. But does it actually compare well in practical? So obviously, on books it's different. That is why we have some bottlenecks in neuromorphic computing in general. So first thing being the rated encoding efficiency. So the spiking neural networks, as of now, they use a rate encoding, which is for the number of spikes over time, and it consists of other stuff like that. But what this does is it increases a major thing, and a major drawback it sets is the increase in latency. So this increases the need for energy, and it also puts a lot of effort on the data that is being provided because the data can only be clean. If the data is a bit different, then it automatically doesn't fare well against it. Next is the imbalance, the data set imbalance, what I told about it previously about the multi-class data imbalance. So in this case, what exactly happens is it cannot handle multiple stuff. It gets overpowered by the late spikes. So to solve this, we need to introduce a solution where like the first spike or the first event, first accurate prediction is given more preference than the ones that dominate the noises that dominate. So next thing is related to the noise itself, where it is very sensitive to the noise. So currently, the standard ANNs, they use spatial dropout to prevent overfitting, but SNNs do not have a way to attack this problem of overfitting. So we cover all these with our solution. And first off, what exactly are we doing in this? So this is a summary of the literature that has been worked on previously. As you can see, some of the papers in prestigious conferences like NeurIPS and AAAI have been worked on, but first paper, this Zhang et al. Has worked on high accuracy and he has produced significant results. But what he has not taken care of is the energy profile and how many energy spikes there are. Next one was actually taking care of the energy, but it did not check for the balance of accuracy. And the paper in NeurIPS by Lee et al. Has actually taken care of both, but it did not give us a balanced result for both of the metrics. Our solution, however, it gives a very good energy profile. So what exactly is our originality or novelty in this? So first thing is we introduce something called as the RTE mapping, rate to time mapping. So this changes the way the rate counting works with the first spike being dominated over the other noises. So this creates a way such that the early noises or the early ones that come in, which are correctly guessed, have more preference over the others. Next is the BTI loss function. So we have introduced a new novel function for loss metric. Here we take care of the rewarding part where we check that the first ones are actually rewarded while the noises that come in later and aren't accurate, which is the noise, is penalized so that we can actually get better accuracy over each round. Next thing is the last research gap that we spotted on the spatio-temporal dropout. So here we have created a new novel masking technique, and because of this, the membrane potentials keep dropping across each of the domains, which is the space and time in this case. Uh, Now, since the space and time neurons have been changed, it can result in beneficiary spikes in this case. Now, how exactly does it help? We look at our main contribution of RD mapping and we check how exactly it's being used. So in this case, the RD mapping works like this. So instead of using a normal pixel intensity, instead of encoding that, we use something called as a time to first spike. So this paradigm changes the whole concept on how artificial neural networks work. So we think of it like a running race, a sprint, where the first one with the winner is rewarded and the last one is actually penalized. So this is the difference between the stronger and the weaker signals. So how does this actually help us? As we can see, this actually helps reward the actually needed functions rather than the noises that are just there for overfitting the model. Next, in the results, we can see that our solution, it has the least number of spikes for inference and gives a balanced accuracy of 92.4%, while also maintaining that the total energy is 1.17 nanojoules. Now, this was obviously worked on a data set, and it was a 10 class FMNIST data set, and the simulation was done on a 45 nanometers CMOS technology. Now, what exactly do these results mean? So the three things that we're overcoming here. First is the late spike bias. So we're ensuring that the late spikes that appear do not actually affect our whole system. And this is being done with our BTI loss function that we've introduced so that each one is penalized over each round. Next one is the trade-off between the accuracy and the sparsity. So this way we are taking care of both the drawbacks as of now, which is a balanced solution to accuracy and energy. Next thing is the robustness. So across multiple classes, it is a 10 class system, a 10 class data set. Across all these, we have obtained a great result, and we have checked the spatio-temporal dropout mechanism, and we've noticed that it did not overfit each one of the in any of these in any of the rounds. So that shows that it's learning instead of just predicting based on the data set itself. What exactly are we targeting with this? We've targeted SDGs 7, 13, and 9. So 7 and 13 being the affordable and clean energy. As we know, energy demand is in the rise. In fact, it is sort of right now more than anything else with the current situation and everything of that sort. Energy is regarded as one of the most important things with the boom of AI too. So we are seeking to provide a consistent hardware system which can actually train models in a much less energy required constraint. Next thing is obviously the industry innovation. So we're trying to build a neuromorphic domain and a hardware which can actually tolerate the system. And as they say, access to clean energy is not a luxury, it's a necessity. This is a famous quote, which is derived from the UN SDG 7. Now, some of the applications of this could be seen in AVs or smart medical wears or UAVs. So each one of these systems actually face a lot of computation issues with our framework. Hopes to solve all of these because even a few nanojoules actually matter, and on a bigger scale, this can actually impact a lot more than what people could think of. Thank you.